Welcome to the last video of chapter 23. Gergő Herángli introduces us to the world of incremental encoders and absolute encoders. The author of the curriculum also describes a lot of interesting robotics application, but for now we will focus on sensors. Encoders are used, for example, to measure the relative displacement or speed of a rotating shaft in industrial machines with high accuracy.
Hi! The simplest case is when you have an incremental encoder. You can find them in robots, on conveyor belts, in printers. Gergő, what are you pulling out of that hat?
As far as I know, it was taken out of a scanner. This is the dial for the incremental encoder. And this is the other part of the sensor. And this one is from a similar sensor, but with a linear design.
Very nice. Let's continue with the incremental encoder. Incremental sensors can be found in applications where high precision is a must. Generally speaking, incremental encoders output a signal proportional to the amount of rotation.
The easiest way to understand the mode of perception is to hold a concrete dismantled device in your hand. On the circular disc, we can see the different line bars equally spaced. These could be small lines made of kitten tears detected by capacitive sensors. It doesn't really matter. The point is to measure some kind of perceptible change. For some reason, optical and magnetoresistive solutions are the most common ones.
In such a simple case, the disc is illuminated from one side and the photodetector is placed on the other side. The signal measured at the output is shown in the figure.
Az ilyenfajta mérés nagy hátránya, hogy ezzel nem lennénk képesek a forgást.
The main disadvantage of such measurement is that we cannot determine the direction of rotation, as the pulse train looks exactly the same no matter in which direction the disk is rotating. To detect direction, more pulse trains are generated by using more light sources and detectors or a single light source with multiple detectors in such a way that the two pulse trains are skewed by 1/4 of a period.
És több fényérzékelőt alkalmazunk, de létezhet több fényforrásos megoldás is. A második fényforrást, vagy ugyanazon fényforrás második érzékelőjét úgy helyezzük el, hogy az általa szolgáltatott impulzusok sorozata az első sorozat periódusának a negyedével legyen eltolva. Így például...
So, for example, if at a certain moment we detect the current leading edge of A and the value of B is low, we know that our axis is rotating forwards, while the leading edge of A and the high value of B will cause the axis to rotate backwards. The signals coming from the disk in the real world are not such perfect square waves as we have shown in the figures. They look more like sinusoidal signals. Analog transmitters are those that do not process these signals, but instead send the near sine signal to the input of the microcontroller. It is easy to understand that for a disk with the same resolution, a sufficiently fast A to D conversion will give a much more accurate displacement calculation.
Sokkal pontosabb elmozdulás számítást tudunk végezni. Impulzusos jeladónak nevezzük.
Pulse transducers are those in which some signal processing, such as comparator processing of individual signals, is performed, so that the digital signal is applied to the input of our microcontroller. Let's talk about how to circumvent the lack of absolute position information. From our previous observations, we can see that using the impulses, we can measure the relative rotation of an axle. To solve this problem, a third signal is attached to the incremental encoder, the null impulse. This is a single marking on the disk, which emits one impulse after every rotation with the length of 1/4 of the period of signals A and B. This gives us one impulse for every round, which gives us exactly the null position.
So, when I apply a supply voltage to the system, I can first measure only the displacement from the initial state. As soon as I first detect the null impulse, not on this dial of course, because there is none on this one, but when I first detect the null impulse, I know exactly where we are.
Perfect answer! Evaluating the signal can be a complex task, especially if we want to get as much information out of them as possible. The basic idea is to count the impulses of A and B signals. We can know the direction because of B, and we can know the revolution because of the null impulse. If during evaluation of one signal we don't take into account the changes of the other signals, we are talking about single evaluation. We can also use double evaluation, in which case we count both the rising and the falling edges of A, so we increment our counter variable twice for every impulse. This obviously increases precision, since we are counting 2 marks inside a single period. The best accuracy can be achieved by quadruple evaluation. In this case, we are counting both the rising and falling edges of both A and B. If we remember, the null impulse is only active for a quarter period, and by quadruple evaluation, we can detect rotations with the accuracy of relative position measurement. The evaluation methods we have discussed so far have the side effect that the impulses are very high speed. Trying to process them in a microcontroller would be impossible. The constant interrupts would load the processor. It would get stuck in the interrupt handler routine. To avoid this, microcontrollers can have a dedicated peripheral specially designed to process signals coming from incremental encoders. This is called the direction detection unit. The direction detection unit can be described as a peripheral which takes the signals of an incremental encoder connected to its inputs, determines the direction of rotation, counts the number of pulses, and detects the null impulse. To do all this, it utilizes a counter, which can be increased and decreased according to the incoming pulses, and set to a value when the null impulse is received. The peripheral can generate an interrupt towards the microcontroller, but it also makes asynchronous non-interrupt related reads possible. The processor can write the counter variable to, which can be useful when loading stored positions. The peripheral can include error detection, which validates the value of the counter based on the incoming impulses and raises an error if an anomaly is detected. For example, invalid counter value when the null impulse is received. To sum up, the biggest advantage of incremental encoders is high precision, which can sometimes mean 50 to 100,000 pulses in each revolution with quadruple evaluation. Every position can be perfectly reproduced, and the measurement is reliable because of the enclosed housing. Integrating the sensor is easy thanks to the integrated signal level matching, and it can be easily used with a dedicated peripheral. The solution has disadvantages too, of course. The main disadvantage is the lack of absolute position, and the need for evaluation circuitry to get absolute position information. Related to this, we can mention that after turning the system on, there is no information about the current position, we need to rotate the axle to get any kind of data. When designing the dedicated peripheral, we must be aware that losing an impulse can cause serious damage. It may take any later position information inaccurate.
Yes, but we also know that there is always another way with some benefits and drawbacks.
Yes, of course, such as the absolute encoders. Absolute encoders are similar to incremental encoders, but they provide absolute position information inside one revolution at any moment in time. This means that position information is available without rotating the axle. This already solves 2 problems we were having with incremental encoders. The difference between absolute and incremental encoders can be easily seen when looking at the disks. The absolute encoder reads a binary number at any position. To do this, it needs as many impulse sources as the number of bits in the position information. In the figure, you can see that along a single radius line of the disk,
Érzékelők a forgás minden pillanatában egy bináris
the markings give a binary number according to the sensors detecting a signal or not.
tartozó érzékelő érzékeli a jelet vagy sem. Az ábrán
In the figure, the outermost ring represents the lowest bit and the innermost ring represents the highest bit.
értékű bitet lehet felfedezni. A legkisebb változás
It means that the smallest detectable rotation is when the outermost ring has a signal level change, while the inner ring will only change after half a turn.
észlelhető ugyanaz. Mivel itt nem csupán egy szám
Since we are not talking about only counting pulses and increasing a counter, but detecting absolute position information, interfacing the sensor is not that easy.
impulzus sorozat továbbítása.
We are not talking about transmitting impulses, but transmitting, in this case, 9-bit numbers. To do this, we usually need some kind of high-speed serial communication.
Modern robotok legtöbb
Most modern robots, for example, use absolute encoders to detect joint position.
pontos visszamérésére.
Köszönjük szépen.
Thank you very much. This gives us a nice and complete picture of the transmitters and brings us to the end of the 23rd chapter of the curriculum. If you haven't seen it yet, watch the theoretical basics in the first video and the numerous sensors in the second.
Szenzortól pedig a második videóban.
Gergő, hadd kérdezem,
Gergely, let me ask you something that's been on my mind. Can all engineers do magic?
tud varázsolni?
No.
Köszönjük szépen.
Thank you very much for your kind attention. Don't forget to subscribe to the channel.
Sok sikert.
I wish you good luck in your studies of electronics. Bye bye!
Sziasztok!
Bye.